about your upcoming projects. Because you actually have the first assignment due tomorrow, but luckily it's a really easy assignment. Yes, all you got to do is click 2 buttons. And if you do it wrong, you can go back and switch your answer later on. I just need you to click the buttons now. So let's talk about the project as a whole, so you guys can make educated decisions. Okay, online people, can you still hear me? Yes, okay, sweet, sweet, okay. So I think it's 30%, it's either 25 or 30% of your total grade is based on this project, which we're going to have instead of having a final exam. And so this is going to have, if you took 220 with me, this is going to have a similar format, but just so everyone knows, this project, the end result of this project will be a 5-minute presentation where you will explain a concept from this class using an analogy or an example. Sound okay? If you did have my class last semester, you don't actually have to make something for this project. You can if you want to. It could be like a great example if you want to do that, but making something is not a requirement. We're just explaining something here. Okay, so so let me actually skip what's due this week and talk about what's due next week. So next week, your outline will be due. And so the way this project goes is next week you'll have to do an outline that kind of outlines your project. 2 weeks after that, you'll have to send in a slide set, so like 4 to 5 slides. 2 weeks after that, you'll do a peer review of each other's slides, so you can kind of get some feedback. And 2 weeks after that, at the end of the semester, you'll turn in your final revised set of slides, and you'll do your presentation. And you will have an option of doing your presentation in class or just posting a recording of your presentation to a forum. Okay, so far so good? All right. So let me actually start here, and then we can go to what's due. Oh, that date is very wrong. I'm gonna ignore that date. But just looking at this, just to kind of describe what this project is. A lot of students do have trouble coming to in this class versus the mechanics course, Physics 220. And one of the big reasons is the mechanics course is very hands-on, right? You can throw something and see how it goes through the air, and you can rub 2 surfaces together, and you can feel the friction. But in this course, we have a lot of really conceptual concepts where, an electric field, and you can't see it. You can see some of its effects if you look closely enough, but it's not as visual, and it's not as hands-on. So what I want y'all to do is I want you to choose one concept from this course, and I want you to explain it how it makes sense to you. And so one way a lot of people relate to these concepts is they make an analogy. So like we talked about resistors in series and parallel over the past couple of weeks. And I use that analogy of cars going down the highway, where if you opened up another lane, there would be adding a branch of your circuit in parallel, and that would allow for more cars to go down the highway. Where the number of cars going down the highway was like the number of electrons, so the current, and the number of branches was like adding an extra resistor in parallel. And so that's an example of an analogy that gets used in this class a lot. You also might want to just use an example. So like with RC circuits, I brought in a capacitor and a light bulb and we watched the light bulb light up. And so that would be an example where you could see the current of going through the light bulb over time and see how it exponentially decayed. And so what I want you to do with your 5 minutes is explain this concept with some analogy or an example that helps it make sense to you. Sound okay? Everyone's kind of with this idea? So next week, you're going to just turn in an outline of your project, 250 words. It will have your concept, a brief explanation of it, and I say an example from your experience, a technological application. I'm not even sure an analog that you can relate to. And then you're going to explain how the example you identified relates to your topic. Okay. Now, this week, what I found, if I let people just choose whatever, I get 60 projects on electric force, which is not fun to grade. So what I make people do is I have a list of topics you can choose from. And I noticed that most people, like lots of these are full, so clearly most people have looked at this. But basically I only let 3 people choose per topic. So 3 people have chosen electric force, 3 people have chosen electric fields. You notice that this list of topics covers not only stuff we have done, but stuff we have yet to do. And so so you can choose whatever you want. The due date for this is Friday night. It's worth 10 points out of a possible 100 on your final project. So this is 10% of that final project grade. Just choose one. Let me tell you, with this project, I generally let people have a couple days leeway with late work, but since each step builds on the step before it, I really don't allow late work past a couple of days because the idea here is I want you to think about this before you write your outline. And I want you to think about your outline before you write your slides. And so if you do it all at once, that's not really a great example of you thinking things through. Does that make sense? Okay. So I also wanted to say, so I know in this, like all the earlier, the stuff that we've already covered tends to get chosen first. But what really gets left out, so like magnetic fields and matter, those are like various types of magnets. That's an interesting topic. Also, Faraday's law and Lenz's law, really good topics. You'll have tons of analogies, you'll have tons of examples and technology. Both of those are excellent topics if you want to choose them. Also, mass spectrometer. If you've ever watched like one of those crime scene investigative police procedurals, they all use mass spectrometers. There's a wealth of technological examples there. And then last of all, the one I would choose if I were doing this is I would choose resonance in AC circuits. Because anything that is a wave is a resonance in an AC circuit, like a spring, a swing, a pendulum. That's a really nice, that has a lot of analogies in it. So that's a good one too, although slightly more in depth. Not as good as Faraday's law. Okay, is that okay? Okay, watch the recording. Which I will have online by tonight, along with Tuesday's recording. Okay, does anybody have any questions? Right, okay, yeah, you watch the recording. Anybody else? Yeah.
This is why we go through and you want to switch your project.
That is fine. That's absolutely fine. Yeah, even if you get to like the slide stage and you're like, oh my gosh, I thought I had a really good thing, but I actually don't know if I want to talk about this. It's totally fine to change your project. The idea here is I want to see you thoughtfully engage with the material, which is why I've got it all spread out, and why, like, overall talking for 5 minutes about something is not, that's not a huge deal, but like doing every step in this project, it's much easier for me to see that, yeah, you've thought about this and you understand at least one concept in this class really well. I should also add that also means that I've spread out the point distribution so that if you wait until the last week of class and then just, have the final project, even if it's a really good final project, you're only going to get about 20% of the points there. So you are getting points for doing every single step of this. Does that make sense? Because I want you to thoughtfully engage with every single step of this. Oh yeah.
So if you do decide to switch, does that mean you have to restart from again?
No, you just have to let me know. Sound okay? Any other questions? My online people? Okay. Yeah, we just did RC circuits Tuesday. And yeah, RC circuits is a good one. Also, if you have any questions about your topics, please do let me know. Okay. Anything else I need to say about this? We're all pretty happy here. Okay, cool. You stay on. I feel like I forgot to tell you something, so I'll probably interrupt myself in a few minutes and let you know what it is I have forgotten. Okay, next thing. Speaking of RC circuits, we pretty much wrapped that up on Tuesday. Your quiz this weekend is over whatever is pretty much over RC circuits, because that's what's left of chapter 10 that we didn't cover last week. Your chapter 10 homework is due this Friday. Would anybody like to ask a question about chapter 10? Yes.
Can we go over number 20 and 22 in the homework?
Almost certainly yes. From chapter 10. View assignments. Number 20, and 22?
Yes.
Okay. Load. Okay. Okay, let's look at that. Might have exited. Oh, no problem. And two, I'm actually gonna get those videos up right after class, so don't stress about it. Okay, this goes here. Here, let's see my screen. Okay. Number 20. 20, chapter 10. Okay, so number, not 23. Okay, so we have a RC circuit. A, B, there's a resistor, there's a capacitor, where if you hook it up to B, you're discharging, and if you hook it up to A, you are charging. This problem gives us the EMF of the batteries. It tells us the value of the resistor. It's in kiloohms. And the value of the capacitor in nanofarads. Now it's going to be initially turned to A. So initially we're going to be charging this. And it says that the switch is left in this position for a sufficiently long time so that the capacitor is fully charged. Okay, so basically we hooked up the battery, the resistor, and the capacitor, and we let the current go until the capacitor was fully charged. Okay, so part A wants to know the maximum charge on the capacitor, in coulombs. Okay, to know that, we have to figure out what the maximum voltage on the capacitor will be. So if we hook up this capacitor to a 4.5 volt battery, what will be the maximum voltage on the capacitor? .5 volts, because the current will go until the capacitor has achieved the same voltage as the battery, and so that will cancel out any electric field, so it'll stop after that. Okay, so we'll have our equation for capacitance, like that, where capacitance is charge over voltage. If we want to know the maximum charge, we need to multiply the capacitance by the maximum voltage. And we know we've hit the maximum voltage when the voltage of the capacitor is the same as the voltage as the battery. And note nano 10 to the negative 9. Okay. Which gives us an answer of about 2.12 times 10 to the negative 6. And what should the units on that be? Say again? It's units of charge. What are units of electrical charge? Think way back to the first day of class. Coulomb. Coulomb is correct. Excellent work. Coulomb. Okay, so that was A. We have the maximum, so after this thing is fully charged, we have 2 times 10 to the negative 6 coulombs of charge on it. So now we have our capacitor all charged up. We're going to unattach this switch. So it was hooked up to A, and now we're going to unhook it from A. But we're not going to hook it up to B. So literally what it looks like is this picture what I have right here, with that switch just not hooked up to anything. When the switch isn't hooked up to anything, what's going to happen to the voltage across the capacitor? And one thing you might ask is, what's going to happen to the charge on the capacitor? Is it going to go somewhere? No, right? I like to know, because it's got nowhere to go, right? I don't have any sort of loop. And so if the charge is going to stay, what's going to happen to the voltage? It's going to stay, because that voltage is generated from the charge on those plates, right? So for part B, the voltage is constant. Voltage does not change. Okay. So next step. Now we're going to hook it up to be like that. Okay, so now we have a resistor and a fully charged capacitor initially hooked up. Now we want to figure out the current. So we'll have some current through the resistor the instant the switch is closed. Okay. Okay. So so if you guys remember, we on Tuesday we hooked up a light bulb and a capacitor and a battery. The light bulb turned on, and then it slowly dimmed over time. And then we took the capacitor away from the battery and just hooked up the light bulb so it attached to either side of the light bulb. What happened then? The same thing. It got bright and then slowly dimmed over time. So when we're looking for the current just when the switch is closed, are we going to be looking for the maximum amount of current or the least amount of current? I think I heard Max over there. Yeah, because that's when the light bulb's the brightest, right? Okay, so we're looking for the maximum possible current here. And the maximum possible current is going to happen when the voltage across the capacitor is equal to that 4.5 volts. I have a resistor, and so we can just do a voltage equals current through the resistor times R. Sound okay? Okay, so I equals V over R. And if we're at the maximum possible spot, that means my voltage across the capacitor is at the largest it can be. And my resistance is 120 kilo ohms. So how many ohms is that? What should I put on the exponent of this 10? What does kilo mean? 1,000. So this should be 10 to the third, right? So the problem gave us that the resistance was 120 kilo ohms. Okay. 4.5, 120 kilo ohms. Okay, this is 3.75 times 10 to the negative fifth, I assume. Yeah, it looks good. Okay, and this is a current, so what are the units on this guy? Amps, I like amps. Okay, that was C. It's a long problem. Okay, then we hit D. And so D, now we're going to start being a little bit sketchy with this. Where D wants an expression for voltage with respect to time across the capacitor. So yes. Excellent. Okay. The voltage, okay, so it wants an equation of voltage with respect to time across the capacitor. As you guys just told me that when you hook the light bulb across the fully charged capacitor, at first it's bright, and then it starts to dim, right? And that's as the charge starts leaving the capacitor, and so the voltage of the capacitor gets smaller along with the current. And so what we can do is we can say that the voltage across the capacitor equals the current through the circuit multiplied by that resistor. Because whatever, if you do like a Kirchhoff loop around this thing, whatever voltage you gain across the capacitor, you need to lose it across the resistor, right? So whatever the voltage across the resistor is, that'll be the same as the voltage across the capacitor. Everyone pretty okay with that? Okay. And you might say, but we don't know the equation of current with respect to time. And I would say, look back to Tuesday's recording as soon as I put it online, because that's what we derived on Tuesday, right? Like we made our loop and we did a Kirchhoff loop and we solved for charge with respect to time. And then we took the derivative of that and that gave us current with respect to time. Everyone looks decently okay with that. So let's write down what that was. So that was, we had this Imax, and then we had our exponential, where this was e to the negative t over tau. And do you guys remember what tau was? RC. Tau was our RC, our time constant. And then we're going to multiply that by R there, because voltage is current times resistance. And now notice here what I have is I have an Imax from part C times R times this time dependent function. And if I have the current times the resistance, what is that really? Yeah. If you multiply current times the resistance, what do you really have? You have a voltage. And if you multiply the maximum current in this situation by the resistance, you really have the maximum voltage across that capacitor, which, as you remember, was 4.5 volts. Sound okay? Okay, so you can say that this is really the battery voltage. I think they want you to put it in as like that E negative T over tau. And I'm betting they want you to put an RC here, like that. Okay, that's the voltage across the capacitor with respect to time. Okay, does that look good? If that looks good, we're looking at part E. Absolutely. Where part E asks, calculate the time in seconds after the contact is made to the switch at position B that it will take the capacitor to discharge halfway. So you hook up the switch to B, you start discharging that capacitor, and we're asking how long is it going to take the voltage to go from 4.5 volts to 4.5 volts divided by 2, 2.25 volts. Sound okay? Okay. We're going to use that equation right there, where we would like to find the time for when the voltage is half its maximum value. And I could even write this fancier. Instead of Vmax, I could write the battery voltage, because we just said that's what the maximum voltage was, right? Yes. Because so the problem is asking us how long it's going to take for the capacitor to lose half its voltage. Okay. And yeah, we're looking for a time in seconds. Well, I'm hoping you're looking at this equation and saying, well, we could easily start right there, where I have my function with respect to time. I want to know when it equals e over 2, so I'll just set my function equal to e over 2 and solve for t. So far, so good. What's happening to my e's in that equation? I saw that. They cancel, right? Okay. So I have 1/2 equals e to the negative t over RC. I need to isolate that t. How do I isolate that t? Maybe get rid of that e. ln. I take a natural log of both sides, right? So I have the natural log of 1/2, natural log of that guy. So I'll have a negative t over RC, or I'll have t equals negative RC times the natural log of 1/2. And you'll plug in your numbers and you'll say, I'm a little uncomfortable with the fact that there's a minus sign out front. But then you'll also say, hey, the natural log of anything less than 1 is a negative number as well. So that'll work out just fine. And for this set of numbers that I'm given, you should get 0.04. And what sort of units on that one? Seconds. Excellent. Excellent. Now, I kind of like you guys to notice that this is a small amount of time here, right? That is because they used much more realistic values for their resistor and their capacitor than I did in class. So I had a 1 farad capacitor. And while I told you that was a large value, let me just tell you, nanofarads or microfarads are a much more reasonable value that you will see in your circuits. 1 farad is big. So with that makes your time constant, the RC, tau, much smaller, which means that instead of being able to visually see the brightness of that bulb die off over time, it pretty much just blinks out. In fact, making an RC circuit out of what you find in your electronics lab is not a great demonstration usually. I've tried. It sucks. Okay, this looks really great. We found the time. So that's how long it's going to take for this capacitor to reach half its voltage. And then the last part F, asks to calculate the current through the resistor at 25 milliseconds after the switch is connected to B. And so again, we're just going to run back to our equation of current with respect to time, which is that guy right there. So our current with respect to time is I max e to the negative t over RC. We calculated the I max right there. So we'll plug that in a second when we need to plug in our number for I max. And if we want 25 milliseconds, I should just plug in the numbers now. What is that? 3.75 times 10 to the negative 5th. 10 to the negative 5th amps. E negative 25 times 10 to the negative 3 seconds, all over this large number, 120 times 10 to the 3rd ohms. That's a 3 on top of that 10. And 470 times 10 to the negative 9 farads. And you play very carefully with all those exponents and your parentheses and make sure you are extremely, just be really careful with all your numbers on that one. For these set of numbers, you should get 2.4 times 10 to the negative 5th amps. I would recommend working out the powers of 10 first, and then working out the digits in front. Okay, and that's the whole thing for 20. Did that make sense? Okay, any questions on it? And you wanted to look at 22 as well?
Yeah.
Okay, yeah, I think after this one, 22 is you're gonna be like, ah, yes. So 22, we have a resistor, a capacitor, and a battery are connected in series, and I'm gonna add a switch to that so we can talk about like closing the switch. They tell us the value of the resistor and the value of the capacitor and the value of the battery. And so we're going to find the initial current. Okay, so this is I have my light bulb, my capacitor, and my battery, and I just hook it up. Is the bulb very bright or very dim? Yeah, I initially just touched everything together.
Right.
Yeah. Okay, so we're at the maximum current, right? And the maximum current occurs when the voltage across this capacitor is 0. So if you're just like looking at the voltage here, whatever voltage you gain across the battery, you're going to drop across the resistor. Okay, which means the voltage of the battery will equal the current through the resistor times the resistance. And so that current will equal the battery voltage over the resistor, and you're just plugging in your numbers to that one. Ten to the negative 2.01, yes. They picked good numbers. What are the units on that? Amps, because it is a current. Okay. Sound all right? Part B wants the time constant, and you guys have told me that the time constant for an RC circuit is just R times C, and so you just multiply those two things together. I have a microfarad. So what exponent should I put on that 10? So what does micro mean?
Let's see.
No, that's an open paren.
Okay.
And I would refer you to the first day of your mechanics course, and maybe the first day of any science course you took, where they talked about prefixes. That's 10 to the negative 6. Never thought that was going to be important, did you? Okay, and 401 times 101 times 10 to the negative 6 is 0.041. And here's the tricky question. From just the givens. The tricky question is, what units am I going to put on this time constant? Seconds. Excellent, excellent. Time constants have units of time. Okay. This is a good one. What is the current after one time constant in amps? So basically they're saying after 0.041 seconds, what is the current in the circuit? So let's look at this. So we know that our current is I max e to the negative t over tau. And so if we want to know the current after one time constant, we set our time equal to tau. And so we have I max e to the negative tau over tau. And what is anything divided by itself? 1. Excellent. So this thing up here is just 1. So we really have I max times e to the negative 1, or 1 over e. And that's just a number. So I have my I max, 0.01 amps, 0.01 amps. I have whatever 1 over e is. And you should get 0.004. And once again, what are the units for this current? Still amps. Excellent. Everyone pretty okay with that? And just so you know, that's usually why when you have these decays, that's usually why when you have these exponential decays, why you measure it in terms of time constant. It makes the math really easy. You know, you can say, where am I after 1 time constant? Where am I after 2 time constants? And so instead of you know, saying a second or 10 seconds or 100 seconds, where your math is going to get funky, you just measure in units of time constants. Which is exactly what they have you do on part D as well, where they ask for the voltage after 1 time constant. Actually, we're going to do this an easier way. The voltage after 1 time constant, I know after 1 time constant we have this current. And so if I need to know the voltage on the, okay, I'm going to have to think a little bit harder. We want the voltage of the capacitor after 1 time constant. Sound okay? And so now we have the current. So I can tell you the voltage on the resistor because I can do V equals IR, right? And so what might be easy is to say, okay, I'm going to do a Kirchhoff loop here where I have the voltage of the battery minus the voltage across the resistor minus the voltage across the capacitor, all adds up to 0. So I have the voltage of the battery minus the voltage across the resistor minus the voltage across the capacitor, all adds up to 0. And so the voltage of the capacitor will equal the difference between the voltage on the battery minus the voltage across the resistor. And we know the voltage across the resistor is just the current times the resistance. IR. And so here's our current that we just calculated for after 1 time constant. Our battery voltage is just the same, 4.01, not 4.5, that was the last problem. 4.01 volts, 0.004 amps times the resistance of 401 ohms. And that will equal 2.5. And what unit should I put on that? Yes, perfect, perfect. Voltage of the capacitor is measured in volts. Okay, first, are we kind of happy here? And so we found the voltage to be 2.5 volts after 1 time constant. Does that make sense given these numbers? I like the nods because we would expect something between 0 and 4, right? And so after 1 time constant, dropping to half the value is pretty reasonable. Okay. Okay. That seemed pretty good to me. Any more RC chapter twin questions in general? Because if you guys are happy with chapter 10, we will start chapter 11, which is a great chapter. Magnets. See, it is a good chapter, right? Okay, excellent. Magnets, chapter 11, I guess. Is it chapter 11? Yes, chapter 11. Magnets. Okay, so we have reached the second half of this semester, where the first half of the semester we talked about just electricity. We started off talking about electrical charges and what happens if they just sit there. And so we said, well, they made these electric fields. They have these electric potential differences. There's forces between the charges. We extrapolated that into some very constant velocity sort of problems where you looked at current, where current was going around a circuit at a constant velocity. Now we're going to add in this idea of magnetism, where we're going to start just talking about magnets, but then the big thing is that electricity and magnetism are really just like two sides of one coin. They affect each other. And there's a reason we call it electromagnetism instead of electricity and magnetism. So for historical context, have you guys heard of like the grand unified theory? It always shows up in like weird like science fiction movies. Okay, the grand unified theory is this idea, is this pipe dream that one day we'll have our four fundamental forces of the universe. We'll just have one equation to explain everything. So instead of having an equation for gravity, an equation for electricity, an equation for the strong nuclear force, we'll just have one equation which encapsulates everything. There's some issues with gravity.
Yes.
But what kind of started this was electromagnetism, where long ago there were equations for electricity and equations for magnetism. And then Maxwell came up with a set of equations that related them, to the point where if you use fancy math, you can just write down one equation. And that explains all of electromagnetism. You have to use fancy math. Not fancy math, you got to use 4 equations. But it combines into one big equation. And so, and just so you know, we've the weak nuclear force that's been, you can write down one equation that it's for electroweak interactions. Strong nuclear forces being thought of, gravity's a loss, is a loss. But we'll work on that. It's being worked on. But electromagnetism fits together really nicely, where electricity is going to affect magnetism and magnetism is going to affect electricity. And you'll see this as we go through here, where you can't really talk about one without the other. So, but let's start with magnets. What do you guys know about magnets? There's a north and a south. All right. What else? Okay. Would you say opposites attract or like attract? Opposites attract. So north and south want to come together, but north and north want to repel, and south would like to repel. Okay, excellent. Let me ask you something. So far, this is very much like electricity, right? Where we had positive and negative charges, and like charges repelled, but opposite charges attracted, right? But so there are a lot of similarities between magnetism and electricity. But the question I was going to ask is, can you have a North Pole without a South Pole? And before you answer, let me ask you a better question. If I have this bar magnet where I have a south and a north, and I just wanted like a North Pole, and so I chopped it in half, would I get just a North Pole?
No.
I like no.
The right side was to be north, but the other side was to create this.
Excellent, right. So I won't have made like a monopole. I will just have made two smaller dipoles. And I could keep playing this game, right? I can cut this magnet a lot. But each time I do, I'm not going to get two different magnets, two different poles. I'm just going to get a smaller magnet, north and south. There's a north and a south there. And I could keep doing this until I get down to molecules. They still have north and south poles. I get down to atoms. I still have north and south poles. I could even split my atom up into electrons, protons, and neutrons. They each have a north and south pole. I could have more fun with this. I could split my protons and neutrons into quarks. Quarks still have a north and south pole. Okay, so down to the level where we cannot split it anymore, things seem to have north and south poles. So we don't see magnetic monopoles. And people actually make a big deal about this because there's no math behind this. Like there's no conservation equation that says, of course you shouldn't see magnetic monopoles. We just don't see them. To the point where people have spent millions of dollars of government money trying to detect them. It's definitely a thing that the question that people have asked, whether or not you see magnetic poles, you don't see magnetic monopoles. Sorry, monopoles. It's a question that people have asked that, you know, maybe they're completely possible. We just don't see them very often, like antimatter. It's a thing that exists. We just don't see it very often. However, even after many years of studying this, no one's ever detected it. There's actually this really famous experiment by Blas Cabrera where he made a magnetic monopole detector. Very legit, by the way. And on Valentine's Day back in like the 1980s, he had one blip on his detector. And it was called the Valentine's Day monopole. And he never found another one. So it's always been assumed that that's just noise. But it's a legitimate field of study. It's extra legitimate because if I have any electrical engineers out there, you can do all this circuit analysis we've been doing using magnetic monopoles instead of electricity. You just slide over to the magnetic domain and you analyze magnetically what's going on in a circuit. It works. It's mathematically very tempting because it just works mathematically. We just don't seem to have any experimental evidence to back it up. Which, you know, we're physicists, so we say you got to have data, but it's irritating. Okay, but we don't see them, so you always have like a north and a south pole. Okay, where that's going to affect things is when we look for magnetic fields. So first, B is the letter we use to refer to magnetism. So whenever you see like a B field, that stands for a magnetic field. So magnetic fields, very similar to electrical fields, except for electrical fields, we had these monopoles, and we kind of built up our fields from these monopoles, right? We said, okay, I know a charge has a field that goes like this. And then we added like more charges, and we talked about how the fields of the two charges would add together. And you could end up with a dipole, or you could end up with a quadrupole or octopole, or however many poles you want, or lines of charges and all that. But it all started basically with this just one point charge. Since we don't have that here, for magnets, what you get are loops. So you don't get these straight lines, you get these loops that go around. And it's very important that they are closed loops. That is also one of those characteristics of magnets. Where on the inside of the magnet, it'll point from south to north, and then it loops around to the outside of the magnet, it'll point from north to south. Sound okay? Okay. Sorry, I'm moving. My notes are all a mess in this chapter. Past the Hall effect. Okay. Okay. And let's take a moment to talk about magnetic fields and matter while we're doing this. I think in lab, I think it's going to take you 2 weeks to get there, but in another 2 weeks, you get to do a nice little exercise involving magnetic fields. So here's kind of the preview. Have you guys ever held a magnet before? How could you tell it was a magnet? Okay, so like you could have this magnet, and if you stuck, say, a paper clip to it, it stuck. Okay, was your paper clip a magnet?
No.
How did you tell?
Because then you can put them in paper clip and something else.
Excellent, excellent. So right now, yeah. Hold that for 2 minutes, because it does like seem to be a little more magnety after you stick it to the magnet, right? This is an important thing, because it's not that the charges go to one side or the other, but all your little magnetic field domains start to align. So this is called a ferromagnet. Ferromagnet. This is called a paramagnet, where you get magnetism from the components. So just like you could take this big magnet and split it into smaller and smaller magnets. The way you get a big magnet is you start with a little bit of magnet parts, and you start building them together. Where the more and more stuff you have that has this magnetic field, the overall larger field you're going to get. And so if you look at a magnet, basically what you have there is you have a bunch of little parts of it, like atoms or electrons. And each one of those little parts has a magnetic field. And for a ferromagnet, all of those fields align naturally. So you have a north side of your object and a south side of your object. Okay, so that's a ferromagnet. Your magnetic domains align just by nature. Then we have these paramagnets. I will draw more of a blob for my paramagnets. And paramagnets, their components have magnetic fields, but they do not naturally align. They're naturally all over the place like that. And so while they have this capability of magnetism, they do not have the structure of magnetism. Which is why if you can impose an external structure to them, like putting them in a magnetic field, they will start picking up those magnetic properties. Because what happens when you put them in a magnetic field, so you put them in some magnetic field, all of a sudden, all their little arrows start to line up along the magnetic field. Now, I'm really glad you talked about charge going to one side or another, because this seems a lot like polarization, right? When we talked about electrical polarization in chapter 1 or 2, or whatever that was, chapter 5, electrical polarization means that you've exposed a neutral object to an external electric field, and the electrical charges have moved to one side or another, or they've aligned, so like your water molecules have a positive and negative side, so they're all aligned. Sound okay? And that way you can have a weak electric field even in a neutral object. Now that's not what's happening here. It's not that I have magnetic charges that are going from one side to the other, because again, I don't have magnetic monopoles. What I have are little magnetic domains that have all rotated so that they're all in the same direction now. Is that okay? And this is why when you put that paper clip next to the magnet and then take it away, it still has that residual magnetic field on it. So for a small amount of time, you can still use it as a weak magnet because all its field domains are aligned. But over time, they'll scatter, or if you hit it against something or drop it, that'll jumble, like you could physically just hit it. That'll jumble the field lines as well. And so it doesn't naturally fall into this aligned state. You have to make it fall into that aligned state, and it'll lose it over time. Okay, ferromagnets versus paramagnets. Now, I like that we have our ferromagnets, and you said that you can put stuff like paper clips next to it, and you'll get some magnetism, but it's a different type of magnetism because it doesn't work just by itself. Have you ever dealt with something that is just not a magnet and never will interact magnetically? So look, say again? Aluminum's a good, actually that's a really good one. I'm gonna start with something simpler and say like a piece of wood. I put a piece of wood next to a magnet. No, there's not going to be anything going on there. But I really like the aluminum. Pennies are a good example too, because these are an example of a metal that is not either a ferromagnet or a paramagnet. So even if something's metallic, that doesn't mean that it's going to have any magnetic properties, even though it will make it more likely. Sound okay? These generally fall into the diamagnet categories. And diamagnets are weird because technically, when you expose them to a magnetic field, they're supposed to try to oppose the B field. But most times you don't see that. Most times what you see is like no reaction whatsoever. So this is generally such a weak response that you don't see it at all. We will talk about superconductors in a few weeks, and superconductors are the one example of a really large diamagnetic response to something, where you expose a superconductor to a magnetic field and it will work as hard as possible to reject that magnetic field. Okay. Does everyone have a decent idea of just like the basics of magnetism in your everyday life? Okay. Like when I say magnet, you know what I'm talking about, basically. All right. Because the first thing we're going to start out kind of where we always start out with the freshman series, with forces. Okay, magnetic forces. Okay, so a magnetic force is weird. It's not like an electric force. So really quick, let me make sure we have our electric force. I'm going to write it like QE. So an electric force is this charge interacting with an electric field. And all you've got to do is you've got to put the charge in the field and you get the force. It's a very simple process. Magnetic forces, or a Lorentz force, as they're Lorentz force, as they're more commonly called, are kind of all over the place. QV cross B. So I have a magnetic field, and I put a charge in the magnetic field. That alone is not enough to produce a magnetic force. My electric charge has to have a velocity with respect to the field to produce a magnetic force. Okay, so if I just put in if I just have my magnetic field and I drop an electron in it, nothing will happen. But even more than that, if I drop an electron in and give it a push so it starts moving, it will experience a magnetic force. However, the magnetic force it'll experience won't be in the direction of the magnetic field. It'll be in the direction V cross B. So we're going to have to do some cross products and right-hand rules to figure this one out. Which, by the way, like half your homework for this chapter is right-hand rules. I'm sure you're very happy about that. Okay, let me write down some basics here. For this, this is the first time we've talked about magnetic fields. We will talk a lot more about magnetic fields in the next chapter and like where they come from and how to derive some equations for them. But for now, just accept that we have magnetic fields, and we'll discuss it in length at some later time. The units for magnetic fields are Teslas. I don't know how he managed to get credit for anything, but he got credit for this, where 1 Tesla is 1 Newton per amp meter. And that it's a weird unit. People, so it's the SI unit, so it's the one we use for this class. People usually measure magnetic fields in Gauss, where like 1 Gauss. Don't hold me to this. But it's about like 10 to the -4 Teslas. But I'm pretty sure my tilde gets me through that one. Where you know, like if you're just looking at the magnetic field of a bar magnet, or the magnetic field of something you hold in your hand, you measure that in Gauss. Once you're up to Teslas, you're talking about like MRIs, or like something where you got to watch your pacemaker because you put out a huge magnetic field. Okay, but since we're doing SI units, we got Teslas. All right, next thing. What you should kind of note from this unit of Teslas is it's a little bit silly that we wrote it down, because what this really is a QV cross B. We just have the units that'll make this work out, so I get newtons on this side of my equation. Also, This is very much a vector quantity. Can't really get much more vector than this cross product right here. Okay. When we get back next Tuesday, we will talk in painstaking depth about right-hand rules and cross products. But what I would like you to think about over the weekend is what a cross product is. Because we kind of have two vector products, two ways to multiply vectors, right? We have the dot product, where you took what's in common or parallel between two vectors and multiplied those. And we have this cross product, where you took what's perpendicular between the two vectors and we multiplied those. So when we say QV cross B, we're saying take what's perpendicular between our velocity and our magnetic field vectors and multiply those. So you don't expect, so when you're looking at this magnetism, you expect a lot of right angles. If you have your magnetic field and your velocity, your force will be in a third direction altogether. And so you have to be really, so all of our problems at this point are going to be very three-dimensional. And you're going to be able to think, nothing's going to run along the field. Everything is running perpendicular. Sound okay? Okay, that's a good place to start, because the next stuff is big. Please don't forget to choose a topic. I'll be like running through that over the weekend. If you don't choose a topic, you lose those 10 points that were so easy to get. Just pick one and hit submit. That's all you got to do. Yes, it says project topic choice. Just click one.
Project topic
Choice.
Oh, choice.
I highly recommend Faraday's Law. It's a good one. And definitely start thinking about what you might use as an analogy. And of course, your Chapter 10 Expert TA and your quiz over the weekend. Everyone good and happy? Okay.